Hello. Well, welcome back to Computer Vision. For those of you who weren't here last time, or maybe who haven't seen me before, I'm one of your TAs. I'm Connor. I'll be doing the lecture again today. Don't worry, Joe will be back on Thursday, so you only have to bear with me for one more lecture. OK, so today, last time we talked about optical flow. Today we're going to talk about a different topic. Today we're going to talk about 3D depth perception and stereo vision. So I want to start a little bit by kind of talking about how do we perceive depth? So how do we as humans, how does our visual system, how do we perceive depth? Does anyone have, I'm sure you guys have ideas. Does anyone want to just say kind of how do you think we perceive depth? Yes. Yes, so he said stereo vision. Any other ways in which we perceive depth? Yes, OK, so he said both focus point, like the focus of our eye lens, as well as the visual size of something. Yes, so he says how quickly things in front of us move as we move. Any other ideas on how we perceive vision or how we perceive depth? Occlusions, yes, good. OK, those are all great answers, and those are all, I have basically all of those listed. One thing we didn't mention, though, but is also how we perceive depth, is binocular convergence. So that is, we have the muscles in our eyes that move our eyes back and forth. So if you imagine, as we're focusing on something, how much our eyes have to point inwards to focus on that thing, gives us a clue of how far away it is. But you also mentioned stereo vision, aka binocular parallax. We have two eyes, we see two slightly different images, and we can tell based on the disparity or how much something moves from one image to the other, how far away it must be. We also have monocular movement parallax, which was also mentioned. So as we move, the things in our environment move as well, and they give us an idea of how far away things are. This is very similar to binocular parallax, but just with one camera or one eye that's moving. We also mentioned some image cues, like, for example, occlusion, or overlapping objects. So we can tell if one object is in front of another object, then it must be closer to us than other objects. Also things like shadows give us ideas about how far away things are. OK, so I have an interactive demo for you guys. It's a really dumb demo, but it illustrates a point, so bear with me. You've all done this before. So I just want to ask you to close one eye. Close one eye. And now cover up Bender with your thumb. And now switch eyes. Open your eye and close the other one. Bender moved. Not a super amazing insight. I'm pretty sure you all could have seen that. But what you have just experienced is binocular parallax. That was a little fun interactive demo. OK, so we kind of have an idea for the rough way in which humans perceive depth. How do computers perceive depth if we wanted our computer vision system to perceive depth? Does anyone have any ideas on what ways which computers have perceived depth? So one way that's used that we just talked about is stereo vision. So here, this is the Z camera that has two cameras and uses stereo vision to perceive depth. But another way that computers perceive depth is using LiDAR, or laser range finding. These are, if you see any of the self-driving cars that drive around, they have those little devices that kind of spin on the top. That's a laser rangefinder, and they use that by bouncing lasers off of objects in the environment and timing how long they take to get back, and they can tell how far away it is. There's also structured light sensors, like this is the original Kinect. And structured light sensors work by projecting a pattern in infrared light out into the scene, and then having an infrared camera that can measure the distortions. And then the Kinect 2, actually, is a time-of-flight sensor. So this is very similar to LiDAR. It just kind of projects out lasers into the scene, times how long they take to get back. This is how computers perceive depth, and we talked about how humans perceive depth. But why would we even care about depth? What usefulness is this from a computer vision perspective? Why can't we just stick with our good old RGB images and be done with it? So there's lots of really cool things you can have once you know how far away things are in your scene. One thing that becomes super easy is object segmentation. So you imagine here, if you, instead of having just RGB images, you have the full 3D points for every pixel in your scene, then if you want to segment all the objects on this tabletop, all you have to do is first use something like ransack to find the surface of the table. And once you've found the surface of the table, you can say, OK, all points above it belong to objects, and then cluster all the points above the tabletop. And now you've just segmented all your objects on your tabletop. This is quite a bit easier than if you're doing it from just regular RGB. We can do other fun things with this. Have any of you heard of Connect Fusion? It was created here between some researchers here at UW and over at Microsoft Research. Basically, what you can do is you can take a Connect camera, connect it up to your laptop, and you just kind of swing it around an environment. It takes 3D images and then builds a 3D model of your environment out of that. And you can actually download the software and play with it yourself. It's for free online. And an extension of that was created by another UW researcher is this thing called Dynamic Fusion. So Connect Fusion worked on environments that are unchanging, that are static. Dynamic Fusion is for objects that move around and deform, like, for example, humans. OK, so here you can see they're shining a depth camera at this person. And while they're shining the depth camera at the person, they're actually building a 3D model of this person. As the camera's moving, as the person's moving, they can use this sort of depth information to build these cool 3D models. OK. All of the self-driving cars use depth information for navigation, so they all use these LiDAR systems on top. And by using this LiDAR system, they can pick out obstacles in the environment, and not crash into other cars or pedestrians, probably a good thing. And finally, the new iPhone X actually has a front-facing depth camera on it, and they use that to do facial recognition. And so you can imagine you could do facial recognition with just color images, but it actually gets even easier and more accurate if you also have depth. Oh, and there's one other cool example, pose tracking. So here's an example. Here's a video from, this is a student named Tanner Schmidt who works over in the computer science department. He made this thing called DART, Dynamic Articulated Real-Time Tracking. And basically, we can use, now that we have the depth information from a camera pointed at our robot here, we can use that to track the pose of the robot over time. Or you could imagine you could use it to track the pose of a person or really anything. So these are all the reasons why depth is super useful. I think depth is really cool. OK. So today, we're going to specifically talk about stereo vision. There are lots of ways in which computers perceive depth, but sort of the traditional one is stereo vision. So stereo vision, we already talked about this. This is the same thing as binocular parallax. We have two cameras offset slightly, looking at the same scene, and we can tell by the disparity how things move, how far away something is. So if we're looking at two images that look like this, what we know about this is that if we're looking at both of these images, the displacement from one image to the other, so how far something moves in one image to the other image, is inversely proportional to how far it is away from the camera. So we know, for example, this bear didn't move very much. It's far away. This little, I don't know what that is, this green thing, it moved a lot, and so it must be much closer. Basically, what we can say is if we can look at these two images and tell where something moves from one image to the other, we can tell how far away it is. So how do we do this alignment? How do we align the two parts of the images? Well, we've already learned one way to do this when we were doing panoramas, and that is feature matching. So we can find a feature in this image, we find the same feature in the other image, we compute how far it moved from one image to the other, and then we can say we can just triangulate it and figure out where it must be in 3D space. So now the question becomes, how exactly do we do the feature matching? Do we use RANSAC like we did for panoramas? Do we use something like a bipartite graph matching algorithm? How do we do this? So the truth of it is, this is actually really hard. So if we just want to find this feature here somewhere in this entire image, doing so is going to be really hard, and it's going to be prone to lots of false positives. So the question is, can we take advantage of the structure of our stereo cameras, the structure of our 3D environment, to make this feature matching problem easier on us? OK, so to do that, I'm going to back up a little bit, and we're going to talk about perspective projection. Now, you guys already talked about this a little bit with Joe. I know that because I stole these images from his slides. So we talked about perspective projection a little bit, but I'm going to go over it again because it's going to be super important how this works for how to do stereo vision. So let's look again at our pinhole camera model. So here's the camera model that we looked at before. And here's our pinhole, our little aperture. And here's our focal length, and here's our image plane. So if we have a real object, this airplane here, it just projects down to the image plane like this. And usually when we're talking about perspective projection, that is projecting this 3D object onto the 2D image plane. We actually talk about it with respect to this virtual image plane, just because it makes the math a little bit easier. So instead of projecting it here and having it be upside down and all weird, we project it here. And this is exactly the same thing as long as it's the same distance from the pinhole. You can see that the math is all the same. And feel free to stop me and ask questions if you get confused. We're about to get in some pretty hairy math, so feel free to ask questions. OK, so let's imagine this is our setup here for our perspective projection. Here's our camera origin. That's our pinhole from the previous slide. So this is that pinhole right there. We call this is our virtual image. Here we set this is called the center of projection, or sometimes also called the principal point. It's basically just the middle of our image. We just cast a line right through the middle of our image. And we set up our 3D coordinate axis in our system here. We're going to set it up such that our z-axis points straight out from the middle of our image. And then our x and y-axis, our x-axis points to the right, and our y-axis points down. And this lines up with kind of what we've been doing with images so far. If you imagine you're looking at this image from behind, when we've been indexing pixel coordinates, our x has been going to the right, and our y goes down. So this lines up with kind of what we've already been doing. Oh, and here, this f is our focal length. And then we've got the height and the width of our image. OK, so here's our setup. Now let's imagine we have some point in 3D space, x, y, z, right here. What we want to know is which pixel does this point correspond to? So where does this land when it projects onto the image plane? So to figure this out, we know that because of our pinhole camera model, all the light rays that pass through our image plane must also pass through our pinhole, which is this camera origin right there. So we can just draw a straight line from our x, y, z point through our camera origin, or our pinhole, our aperture, and wherever that crosses this image plane, that's where it lands. That's which pixel it hits. OK, so the problem is, given x, y, z, and our focal length, the width of our image, the height of our image, find the pixel coordinates I and j that this lands at. We can compute this using a notion of similar triangles. So you'll notice here, if we're looking at this straight from the side, so let's collapse the x-axis for just a minute and look at only y and z. If we're looking at this straight from the side, we notice we have two triangles here. We've got the triangle that goes from the origin up to our pixel, back to our center of projection, and over. And then we've got our triangle that goes from the origin to our 3D point, back down and over. And these triangles have the same angles, which means they're similar triangles. And because they're similar triangles, then we know that there's a relationship between the lengths of the sides on these triangles. So we know that, for example, this value here, if the value from our 3D point down to our center of projection is y, so this is our height, and then this value from here to here is z, this is just defined by our coordinate system, x, y, z, we know the ratio between those two must be the same as the ratio between these two values. So the ratio between this side and this side is the same as the ratio between this side and this side. And this here is going to be j minus our height over 2. So here, our center of projection is in the center of our image. So we're just kind of recentering our origin to be in the upper left. And then this is going to be our focal length. That's the distance from our origin to the image plane. So we know that the relationship between these two must be the same. So if we want to, we can just solve for j. But there's a little bit of a problem here. And it's that here we go. It's that our j is in terms of pixels. So we've been indexing the image in terms of pixels. However, our focal length, our y, and our z are all in terms of meters, or whatever unit of measure we're using in the real world. It doesn't have to be meters, but it usually is. And so we need to convert our units here. And so usually, we'll do that with something called the pixel pitch, which is going to be the width of our image in pixels, that's divided by the width of our image in meters. This is here we're assuming our pixels are square, which I've never seen a camera with non-square pixels, so I think that's a safe assumption. So we'll just for the moment assume our pixels are square. So our pixel pitch is basically the ratio of pixels to meters, or how big a pixel is in terms of meters. So all we have to do is multiply our focal length by our pixel pitch. So this gives us our focal length in terms of pixels instead of terms of meters. And now we can relate these triangles and solve for j. I will point out that a lot of times, if you look up the focal length for given cameras, they'll just give you the focal length in terms of pixels. So they sort of pre-multiply that p times f. So just pay attention to the units whenever you're looking up the focal length for a camera. OK, so we can just solve for j. And we can do the same thing if we look down from the top. We get the same similar triangles set up, so we can solve for I. So given an x, y, z coordinate location and these camera parameters, we can compute the pixel location where this lands. OK, so I will point out that these parameters are usually called the camera intrinsics. These are the just parameters of the internal parameters of the camera, the focal length, the width and height of the image plane, and the pixel pitch. OK, so now we can go from 3D coordinates to pixel coordinates. Can we go the other way? Can we say, given the pixel that this lands on, can we go, and the camera intrinsics, can we go back and figure out the 3D coordinate? And if the answer was yes, then this would be a very quick lecture. But the answer is, nope, we can't do that. Because this problem is underspecified. We have this pixel where our 3D point lands, but if we don't actually know where our 3D point is, it could be anywhere along this ray out to infinity. So it could be anywhere. So we don't have enough information to figure this out. But if we're given one more piece of information, we can figure this out. And that piece of information is the depth. That is, how far away is this point from the camera? And so here, when we say depth, we're talking about just the z value. So basically, if we're given the z value of this coordinate, then we can just flip these around, these two equations up here, around and solve for x and y. Just like that. So this is going to be super important to understanding how stereo works. But basically, the idea is we can go back and forth. Given the depth value, we can go back and forth between 3D points and pixel coordinates. And I will point out, I think when you guys talked about this before, you talked about it in terms of homogeneous coordinates. I'm not a huge fan of homogeneous coordinates because I think they unnecessarily complicate things. But you can also do this with homogeneous coordinates. Actually, we're going to talk about a different type of coordinates. So we're going to add some more, I would say, necessary complications to this. So we're going to talk about image coordinates. So up until this point, I've been talking about things in terms of pixel coordinates. And so if you recall, in our images, the origin of our image is always the upper left. And we go to the right for x and down for y. So the pixel coordinates here, I and j, specify some pixel in our image. I'm going to define another type of coordinate that also describes I and j. And this is going to be called image coordinates. So image coordinates define 3D coordinates on the infinite image plane. So image coordinates are full 3D, but they lie on our image plane somewhere. So they're technically in 2D, but also in 3D. And our image coordinates are going to be in terms of meters or whatever our unit of measure is in 3D space. So we want to know what is, if we're specifying their sort of these 2D points, or these 3D points fixed to a 2D plane, then what is z here? And for image coordinates, so our image coordinate is going to be this guy right here. That is, our image coordinate is basically the 3D point where this line crosses the image plane. So x, y, z. And so in this case, our image coordinate, our z here, is just going to be the distance from the origin to the image plane, which is our focal length. So here we just set in image coordinates, we set x, y, focal length. OK, so that looks like this. So if we want our image coordinates, then you can think about this sort of an intermediate between the full 3D coordinates and the pixel coordinates. They're sort of halfway between. So if we just describe them like this, here I'm using an apostrophe to describe the image coordinates. Then we can go between our pixel coordinates and our image coordinates just like this. OK, and you can think about this going between image coordinates and pixel coordinates in terms of sort of a rescale and a shift. So basically what we're doing here is we're rescaling it. We're converting it from meters to pixels. And then we're shifting the origin to being in the upper left instead of being in the center. So image coordinates are just sort of a more convenient way of doing the math on the image plane instead of using pixel coordinates. We're actually going to do one more thing. We're going to use something called normalized image coordinates. So normalized image coordinates are basically where we abstract this even one more layer out, and we sort of pretend that the image plane is exactly 1 unit distance from our camera origin. And so our image coordinates here are just going to be x over z, y over z, and 1. And then we just sort of, to go back to pixel coordinates, we just sort of push that focal length up here into the computation for pixel coordinates. So here, our normalized image coordinates are sort of a halfway point between full 3D and pixel coordinates. And they're going to make a lot of the math coming up much easier. I would also like to point out that the relationship here between the full 3D coordinates and the image coordinates is simply take the image coordinates, normalized image coordinates, multiply it by the z-value, and you get the full 3D point. This is exactly the same setup as homogeneous coordinates, so it's very related. OK, so now we know how to do perspective projection. We can go between our full 3D point, our normalized image coordinates, and our pixel coordinates. And all three of these are going to be important here in a second. So let's imagine we have a stereo setup. So we've got two cameras here, camera 1, camera 2. Here's the origin for camera 1. Here's the origin for camera 2. And we have an image plane for each. OK, and let's assume for right now that we know the transformation between these two cameras. We know the rotation and the translation between the origin of these two cameras. So if we have some 3D point here in space, and we'll say I'm using these little 1 indices to indicate that it's in reference to camera 1, then if we want to make this 3D point with respect to camera 2, we just multiply it by the rotation, add the translation, and now it's with respect to camera 2. So we can take 3D points, and we can go back and forth between the coordinate frame of camera 1 and the coordinate frame of camera 2 by using this rotation and translation. And we just learned how to project these down onto the image using normalized image coordinates. So we can also take these 3D points and project them onto the image with our normalized image coordinates. Now what about the opposite? So here we're assuming we start from a 3D point, and we want to know where it lands on the image. What if we start the other way? What if we start with the 2 points on the image, where it collides here with the image, and we want to know where the 3D point was? Well, we know our 3D point is going to be somewhere along this ray here, along this line. And we know it's going to be somewhere along this line. And so all we have to do is just project those lines to infinity, figure out where they cross, and that's where our 3D point is. What this looks like mathematically speaking is a little bit like this. So in 3D, we're going to represent a line as two things, as a point on the line, and then the slope of the line times some parametric value. So here, for every point on the line, there exists some s that when you multiply s into this equation, that gives you that same point. So this is our equation for the line. So we have two lines. Our first line here is this one. So this is our line from camera 1. It goes through the origin. That's our origin. Multiply it by our whatever parametric value times our slope here is going to be just our normalized image coordinate, because we know that our line goes through that point. And then we do the same thing for line 2. But line 2 is going to be in camera 2's coordinate frame. So we just convert that back to camera 1's coordinate frame by doing this. So here we're just using our translation and our rotation to convert it back to camera 1's coordinate frame. So now we have two lines, and we need to find their intersection. Recall that I said, remember that the going between our normalized image coordinates here and our actual full 3D coordinates is just multiplying by the z-value. And you'll notice in both of these cases, in both of our lines, we have some number times our normalized image coordinate, some number times our normalized image coordinate. So this is actually turns out to be exactly the same as our z-value. So we can just sub in the z-value here, the full z-value, z1 and z2. And then we can just set these two equations equal to each other because we're looking for the intersection and solve the system of linear equations. Cool. And actually what will happen in practice is that if there's a little bit of noise, the two lines you have won't actually intersect. So what you want to do instead is solve the least squares. So find the closest point where they get closest to each other. And the reason I'm not going to go into any more detail on how to actually do this is because no one actually does this in practice. There's a fun way to make this much, much simpler, and I will get to that in a minute. OK, so let's go back, and let's say this time, instead of having both image coordinates, we only have one image coordinate, and we want to figure out where the other image coordinate is. And then once we know this other image coordinate, then we can solve the full 3D point. So recall that I talked about that if we just did feature matching alone, that doesn't work that well. So if we just try and say, construct a feature descriptor around this point, and then look for that whole feature descriptor across this whole image, we're going to get a lot of false positives, and it's not going to end up giving us that good of depth perception. So instead, what can the geometry of this scene tell us about what's going on here? So if we wanted to know, what do we know about where this point must be? Yes? Yes. Yes, exactly. There is a line. So if we take this ray here, and we project it on this image, what we get is a line. And we know that our full 3D point is somewhere along this ray, which means our 2D point on this plane must be somewhere along this line. This line is called the epipolar line. And it's just because it'll be the line where our corresponding point is on this image. So unfortunately, though, we can't actually say anything more. Given only the geometry of this scene, we can't actually specify exactly where that point must be, but we can say it has to be somewhere on this line. So then what we can do is we can actually search for the features along this line. And searching for features along a line is much easier than searching over the whole image. So if we do our feature matching here, we come up with our descriptor for this point, and then we slide it along this line, that's going to be a lot easier and have a lot fewer false positives than if we had to slide it over the whole image. OK, so given that if we can figure out this line, we can then try to do feature matching across this line. And once we find the corresponding point, we can compute the corresponding 3D location from that. What we need to know then, the last bit of information we need to know in order to actually compute the full depth is how do we know what this line is? How do we compute the equation for this line? OK, so I actually looked through a ton of slide decks to see if anyone had come up with a really good way of explaining how to compute this line. And it turns out that everyone sort of all explains it in the same way, and I wasn't terribly satisfied with how they explained it, so I came up with my own way. So you guys get to be my guinea pigs. I hope it makes sense. OK, and feel free to ask questions if it doesn't. So one thing we know about this line is we know that any point along this ray, if we project it on this image plane, must then lie on this line, because this ray projected on the image plane is this line. So do we have any points that we know are on this line? Yes. This one? Yes, good. So he said the origin here and also the pixel it corresponds to. Yes, that is exactly correct. We know that both of these points must lie on this line. So if we take both of these points and we project them onto this image plane, now we have 2 points. And recall that 2 points defines a line. So now we can use these 2 points to figure out the equation for this line. Interesting fun note here. So we know that this point, any point along this line will project down onto this image and be on this line. But the origin here is an interesting special case. So we know that every single ray that goes through this image plane for every single pixel will all go through this origin, because that's our pinhole camera model. All of them have to go through this origin, which means every single ray goes through there, which means every single epipolar line that we make will have to go through the projected version of this origin here. So if we plotted all of the epipolar lines, they would all kind of be coming out of this origin here. So this is called, when you project the origin of one camera onto the image plane of the other camera, this is called the epipole, which is where the name epipolar line comes from, and epipolar geometry. OK, so let's actually do some math now. Let's figure out how to compute this line. So here are our equations. This is a little side effect of me not liking homogeneous coordinates, but I swear this is going to go away in a second. So here are our two points. So we start with our normalized image coordinate here, x prime 1, y prime 1, 1. Then we need to convert that to the second coordinate, the second camera frame. So this is with respect to the first camera. So we just multiply it by the rotation, add the translation. Now it's with respect to the second camera. And then finally, to project it, remember the relationship between our full 3D points and our projected points is just we divide by the z value. So here, this is a little wonky way of noting it, but z double prime is just going to be the z value after we've transformed this point. It's going to go away here in a second. And we can do the same thing with the camera origin, so that's all zeros. And then we translate it again. And we actually can simplify the one on the bottom, because this is all zeros. Anything times all zeros is just zeros. So we get the translation here, and then we divide by the z component of the translation to give us the projected point. This is actually the epipole. OK, so now we have our 2 points. Let's look at the equation for a line in 2D. So we're looking, our epipolar line is going to be a 2D line. Normally, our equation for a line is this, y equals mx plus b. And this works pretty great when we're describing linear functions. But there's a problem with this when it comes to epipolar lines. Did anyone notice what the problem here is with this? OK, I'll just tell you then. It doesn't handle vertical lines. So normally when we're describing a function that's a line, we're just sort of describing a function as input of x. But here, our line is not a function of x. It's just an arbitrary line that can be anywhere, including it can be a vertical line. And so we can't represent a vertical line with y equals mx plus b, so we need a different equation for a line. So we're going to use this equation. This equation, ax plus by plus c equals 0. Any xy that satisfy this equation are on the line, and any xy that don't are not on the line. We can also write this using a vector notation as the dot product. So here if we take a, b, c, these are our three coefficients, and we multiply a vector x, y, 1, so we just add the little 1 here on the end of the vector, then that should equal 0. So these two, these are two ways of representing the same line. Okay, so we have our 2 points here. These are our 2 points, big, complicated, messy equations for our 2 points that we know are on the line. Note that both of our projected points, because they're in normalized image coordinates, have the format x, y, 1. Because remember, normalized image coordinates means we're pretending the image plane is 1 unit distance from the camera origin, so z is always going to be 1 for our normalized image coordinates. So we could pretend that they are basically points in 2D. And actually, we don't even have to pretend. They really are points in 2D. They're points in 2D on the image plane. So here are our 2 points. Okay. Feel free to stop and ask questions if this gets confusing. So that basically means if we plug these 2 points into our equation here, so here we're using the vector notation again, take the dot product of our ABC times our first point, that should be 0. ABC dot our second point should also be 0. Okay, so what do we know about vector notation? If we have some vector dot with 1 point and that's 0, and the vector dot another point is also 0, what does that tell us about the vector? Can anyone say what we know about this vector? Yes, exactly. So we know that ABC must be orthogonal to both this vector and to this vector. If you're paying super close attention, you'll notice there's actually a degenerate case where if point 1 and point 2 are parallel to each other, then this doesn't have to be the case. Yes? You were one slide ahead of me. Yes. OK. Yeah, but we don't have to worry about that degenerate case in our case because of the way the geometry works out usually. So what he just said is if we want to know what ABC is, since it has to be orthogonal to this point and to this point, we can just take the cross product of the 2 points, and that should give us our ABC. So all we have to do is take, this is our epipole, our camera origin projected into camera frame 2, and our image coordinate projected onto camera frame 2, and we cross product them, and we get the equation for our line. OK, so let's rearrange these terms a little bit. First thing I want to do is pull out these really wonky 1 over scalar values here. We're just going to kind of put them over on the side. Then let's shift this all back to the top because I ran out of space on the slide, so we're going back to the top here. Next, let's distribute this cross product inside of these brackets just to make things a little bit easier. So fun note, if you take a cross product of a vector with itself, it gives you 0. So t cross t goes away, and we're left with this. So now we distribute this inside. This becomes 0. So now we've got t cross our point. So recall, this is our equation for our line. Now if you note, if we take our coefficients and we multiply them all by some scalar, all by the same scalar s, then what we get is the exact same line. So we can multiply everything by some scalar s, and we get the same line. So what this really means is the way we specified our line actually has an infinite number of ways of specifying the same line as long as they're all just sort of scalar multiples of each other. So what this means for our equations here is that scalar multiples, when we're computing this line, actually don't matter. So we can actually just get rid of this scalar multiple over here. Because this is just multiplying by the z value, or dividing by the z values, which if we multiply it over is just multiplying by the z values. And like we said, multiplying by a scalar for this equation of a line doesn't matter. So it goes away. And we're left with this. This is our equation for our line. We have our normalized image coordinates of the point we care about. And we take that, multiply that by our rotation matrix, and cross product the result with our transform, and that gives us our ABC. So this thing here is called the essential matrix. It was developed by Longet and Higgins back in 1981. And it's basically what we can do is we can compose the cross product of T and R into a single matrix Then we can pre-compute this matrix and just multiply it by our x, y, 1 beforehand to get our ABC. OK, so here's how we write this essential matrix E times x, y, 1. So this is the equation for our line. So this is our epipolar line for our corresponding point over here. So let's look at some examples of what this would actually look like in real images. So here, if we have two cameras pointing at this vase from two different angles, we pick these feature points here and look at the corresponding epipolar line in the other image, you can see that the corresponding feature point always lies on that epipolar line. Let's look at some more examples. OK, so here we have, again, left and right images. Here are the feature points in our left image. Here are the corresponding epipolar lines. Here are the feature points in our left image. Here are the corresponding epipolar lines. Interesting to note, this one on the bottom here has these lines are horizontal. That seems super handy. Maybe we can make that a thing. OK, so I said this was going to be actually a lot easier. So we just went through all of this super, super complicated math. But in practice, no one actually does any of that. There's a much, much easier way to do it. And it all hinges on exactly one thing. If you have your two cameras, if they have parallel image planes, then this makes everything so much easier. So here, when I say parallel image planes, what I basically mean is there's no rotation. So this is the identity matrix. There's no rotation between the two. And the only translation is just some delta x, some shift in the x coordinate. But there's no shift in y and no shift in z. OK, so now let's look at this case. Let's say we've got some feature here, x1, y1, 1. So we've got some point on our image that we care about. Let's project our array. What does the epipolar line look like in this case? Anyone have any thoughts about what this line might look like? Yes? Yes, so he says it'll be parallel to this purple line, and he is correct. It will be a horizontal line. Let's actually derive this from the math. So if we recall, here's what our equation for the line looks like. T cross r times our points on the first image plane gives us the equation for our line. Let's plug in our translation and rotation. Here, since the image planes are parallel, our rotation is just the identity matrix, and our translation is just an x value followed by 0 and 0. Any vector times the identity matrix is just itself, so we can just drop that out. And then if we actually multiply out this cross product, what we get is something that looks like this. So here, this is the equation for our line in the case where we have parallel image planes. And if we actually plug this back into our original equation for our line, ax plus by plus c, so we plug in these coefficients here, here, and here, and set it equal to 0, what we get out of this is our y value equals our y value in our first image. So what we get is a horizontal line where the y value of the horizontal line is just the same y value as our first image, which looks like this. So here, the epipolar line now is a horizontal line, and it has the exact same y value as the y value from our first image. So when we have parallel image planes, then it is super easy to compute where this epipolar line is. We just take the point where we start from here and say the horizontal line at the same y value in the other image is our epipolar line. That's it. We don't have to do any cross products, any matrix multiplications, nothing. That's all we have to do to compute that line. And the cool thing about this is it gets even easier. So remember before, now once we find this line, we want to scan across the line to find the matching feature. Well, it turns out scanning across a horizontal line is much, much easier than scanning across an arbitrary line. With an arbitrary line, you have to kind of rasterize the line as you go through all the pixels. With it. With a horizontal line, all you have to do is go across just the row of pixels, and that's it. Very easy. Let's look at one more case where this actually makes life super, super easy. So this here, what we're looking at here is going to be the same as this. So it's just our camera set up here with parallel image planes. But now we're going to look down from the top. So our image planes have just kind of flattened into these lines. But we're looking down from the top at our setup here. And so here what we know is the distance from this camera origin to this camera origin is delta x. And let's say we have some point in 3D space, and we want to know where this point is. So if we start from knowing, let's say we know our original point that we care about, and let's say we've done our feature matching and we found the corresponding point over here that we care about. So now we have our 2 points, and we want to compute the 3D point in space. Then we can notice some interesting things about this setup. So first of all, we'll note that the z value for this point here is going to be the same in both camera frames. Because these camera frames are parallel, then they have the same z value. We'll also note that this distance here from here to here is x1, and the corresponding distance here to over here would be x2. We know that the distance from here to here is x prime 1, x prime 2, and so we can use the same similar triangles notion as before. So we know that this triangle here, this little triangle down here in the corner, is going to be a similar triangle to the big triangle up here. And so we can relate their two sides again. So we'll say that the length of this side, x1, over the length of this side, z, is the same as the length of this side, x prime 1, over this side, 1, which is our normalized focal length. We can also do the same thing on the other side. So we can say the length of this side, x2, over the length of this side, z, is the same again as x prime 2 over 1. Okay, and if we now here what we have in these two equations is we've got two unknowns and two equations, or three unknowns and two equations. We actually have only two unknowns, since we know that these two camera frames are just shifted off by a delta x, then we can say x2 is actually equal to x1 minus delta x, so we can just sub that in place here. So now we have two equations, two unknowns. We can solve each equation for x1, so x1 over here equals x prime 1z, x1 over here equals x prime 2z plus delta x. And then we can just set those two equal to each other and solve them for z. And once we get the z value, now we know the full 3D coordinates of this point. So our z value here, if we solve for it, oh, sorry, here there's a bit of, it's Google Slides rendering incorrectly. I'm putting this delta x on the next line, but this delta x should be over here. Okay, so what we get is delta x divided by x prime 1 minus x prime 2 equals our depth, our z value. And so what this is called here, this on the bottom is called the disparity. So our distance between our cameras, also known as the baseline, divided by our disparity, the change in pixel coordinate, in x pixel coordinates from one image to the other, gives us how far away it is. So now computing our depth value, our z here, is significantly easier than it was in the general case where we have to take two lines, then we have to solve this least squares to try and find where they intersect, where they get the closest, and then that's much harder. Here, it's literally x coordinate in the first image minus x coordinate in the second image, and then divide that into your delta x, and you're done. That's it. You've computed your depth value. So let's look at an algorithm, some just pseudocode here, to actually do the stereo vision computation, assuming, again, these parallel image planes. I'm going to add another assumption. Let's assume the cameras have the same intrinsics, so they have the same focal length, the same, yes? Yes. So parallel image planes, I'm hand-waving a little bit here when I say we have parallel image planes. I'm saying they're only shifted off by some delta x, which necessarily means they're also coplanar. But yes, he's right. So technically, these are parallel and coplanar. Parallel and coplanar don't fit in a title. So that's just keep in mind that's what I mean. OK, so here's a really quick algorithm to actually compute the depth, the z value, for every single point in an image. And here we're going to assume that the cameras have the same intrinsics, the same focal length, the same width, the same height, the same pixel pitch. So basically, we have two copies of the same camera. OK, so we want to compute the depth given image 1 and image 2, given our delta x. This is the distance between the two cameras. It's also referred to sometimes as our baseline, given the focal length and the pixel pitch. OK, so we're going to compute the depth for every single pixel in our image. So this is going to be dense. So we're going to start with a depth image that's going to be the same size as our first image, and our first image and our second image are going to be the same size because we're assuming, again, same width and height. OK, so we're going to iterate over every single pixel, ij, in the first image, and we're going to get some sort of a feature descriptor for that pixel. So this is get the feature descriptor at pixel ij in the first image. And then we want to iterate over that epipolar line. Now remember, our epipolar line is literally just the same y value as it is in our first image. So what that means in terms of pixels is we can go to the same row of pixels, the jth row of pixels in the second image, and just iterate over that row of pixels. So here we're going to iterate over every I prime, so every pixel in that row of pixels. And what we're going to do is we're going to get a feature descriptor for each one of those. We're going to score the match between the two feature descriptors, so our original feature in the first image, our feature in the second image. We figure out which one is the best score. Once we've found the best one, we can again compute our depth here. And here we're multiplying this again by the focal length and the pixel pitch just to convert excuse me, our delta x from meters to pixels. Do you have a question? I hear questions. Yes? That is a great point. He said, I would imagine that most pixels would have bad feature descriptors, so it would be very difficult to find them in the other image. Yes, that is a great point, and I'm going to get to that here in about 4 slides. OK. For now, just hand wave, assume this works. So what I can point out to you about this is 14 lines of code. Pseudocode, but code. So having parallel image planes makes things super duper easy. Imagine how much more complicated this would be if in the general case. So here we have to first compute the epipolar line, which again is that matrix multiplication. Once we've computed that, then we have to figure out how to travel along that line, to scan along that line for each of the pixels that we care about. And then once we find the best matching pixel, then down here we have to solve a least squares problem to try and find where they overlap. But if we have parallel and coplanar image planes, then this becomes super easy. And I know what you're all thinking. What are these? What does it mean to get a feature descriptor? What does it mean to match the features together? And what I will say is we're going to talk about this very soon, but not yet. I want to talk about something else first. OK, so you see how much easier it makes life when we have parallel image planes. So in fact, it's so easy that people have actually spent quite a bit of effort in the literature figuring out how to take the general case and reduce it to the parallel image case. So basically what they want to do is, given the general case where we just have 2 arbitrary cameras pointing at the same scene, can we actually pretend that they are parallel cameras like this, and then do all the math as if they're parallel cameras and not care that they're not parallel? And as we know, we already did this, and you guys are doing it right now in the homework, how to go from one image plane to another image plane. That's sort of off by a shear and affine transform. And we can do that using homographies. So basically, we can compute a homography to go from this image plane to this image plane. And then we have 2 parallel image planes. And we can use that simple algorithm to just solve everything. This is called stereo image rectification. And it is described in a paper called Computing Rectifying Homographies for Stereo Vision, published back in 1999. When I was going through every other slide deck I could find to try and find if anyone had a really good way of explaining this, it turns out when everyone describes this, they don't actually bother explaining it. They just say, here, go look at the paper if you want to figure out how this works. So I went to the paper to figure out how it works. It is super, super complicated, way more than we can cover in a single lecture. So I will say this. If you really, really, really want to know how this works, you should go read the paper. So I'm going to pass on that too. But the nice thing is you really don't need to know how this works, because for basically every stereo camera vision system you will encounter, like that Z camera I talked about way back at the beginning of lecture, they purposely set up the cameras so they're already parallel, because it makes life so much easier. So you don't have to deal with this. Usually you won't have to deal with this. Sometimes you will, but usually you won't. OK, so let's get back to actually doing some feature matching. So if we have, say we've got our 2 images. Here are our 2 images of President Lincoln. We've got our feature in the left image, and we've got our epipolar line. How do we actually figure out which feature there best matches? The standard way of doing this is to take an image patch around our point here, and then as we scan along here, take an image patch around every point we're testing against, and then come up with a matching cost between these 2 image patches, and take the one that has the lowest matching cost. So the default way of doing this is just the sum of squared differences. We literally take this patch, subtract the patch we're comparing against, square it, square all the values, and sum it up. And that's how we get our value here. The other way that we've also looked at in this class is using the cross correlation. So it's very similar. You can kind of do the same thing. And so if we use one of these 2 methods, these are just sort of the simplest way of doing this. If we use one of these two methods, we get a result that looks kind of like this. And as he pointed out, as person up front here pointed out earlier, if we have bad features, we're going to get bad matches. So you can see here, there's like, this is the ground truth from our data. And this is what we get using this window-based search. We get some data that's correct, like the front of the face here. We get most of the lamp, some of the background. But we have these huge chunks of just not very good at all. OK, so we're going to look at here in a second at some places where this algorithm fails. But first, I want to show you this really cool video. I'm going to warn you, this is a promotional video put out by Mercedes. So kind of ignore all the sales nonsense that's going on in there. But pay attention to the camera system underneath, because I think it's very cool.
Traveling and working at the same time. In the new S-Class, passengers have the option of enjoying a completely new level of comfort. Mercedes-Benz now offers Magic Body Control, a world premiere thanks to the first ever predictive suspension system. The unique aspect of our predictive suspension system is that we now use stereo cameras to scan the road surface in real time up to 15 meters ahead of the vehicle. This function is known as the road surface scan and truly is a world premiere. We are the first to do this and to do it in real time on board. It's never been done before. The stereo cameras measure the height of obstacles with a precision of 3 millimeters or better, and at speeds of up to 130 kilometers per hour. In the second step, the measurement data defining the exact road profile is passed on to the suspension system. And thus, the active suspension system knows ahead of time which bumps it's about to drive over and can adapt so that the body glides far more smoothly over the road than a conventional vehicle. As such, the suspension system can actively compensate for uneven surfaces. This prevents the body from oscillating and vibrating. Mercedes-Benz expands the familiar active body control with the road surface scan, and thus achieves a new dimension of passenger comfort.
OK. Yeah, you can see they were really selling their own stuff there. But I think the underlying system is super cool. You notice how they're able to take these stereo cameras on the front of the car and figure out where the bumps are, and then automatically adjust the suspension so you kind of glide over the bumps. It's very fancy. Yes? I would imagine that your headlights would light up the road enough. So I guess it would work. I don't think the marketers would tell us it wouldn't work if it doesn't work. Yes? So it depends on the kind of infrared camera. For infrared camera, you still need a source of light. So yeah, you'd have to have something projecting light out in the scene to see. So like usually an infrared camera, for example, like in my research, I use an infrared camera to detect hot things in a scene. So hot things emit infrared light, but it's a different wavelength than other types of things. And I don't think the road tends to be that hot. So what you could do is you had like a infrared headlight so that a person wouldn't see it, but you could use the camera to see that. But I would imagine in this case, you could use just your regular headlights would work. OK. Let's look at some effects of the parameters that we choose. So one thing I mentioned is that we pick a window around the feature that we care about, and we come up with a feature descriptor based around that patch that we picked. But how big of a window should we pick? Should it be a little window? Should it be a big window? What are the trade-offs between these two? So here you can see we've got two images, left and right image. This first depth image is produced by using a small window, a little 3x3 window. The second is produced by using a large window, a 20x20 window. So the nice thing about small windows is they give you a lot of precision, because you can really kind of see only the feature that you care about at that particular point. So they have more detail, but they're super sensitive to noise. On the other side, large windows are much more robust to noise because they're bigger, so they give you kind of a better perspective on what the feature you're looking at is, but they also give you a lot less precision, so a lot less detail. So here you can see this is the difference. With a small window, it's very noisy, but you get, like if you look at these trees, you get a much better kind of layout of what the trees look like, without the noise, of course. Here you have much less noise, but then again, the trees are much more blobby. Yes? You could. So that's something. So he asked, could you use different sizes of windows and do sort of an average? You could try something like that. Stereo vision is something that's been around for a long time. So you notice that I pointed out the citation for the essential matrix was all the way back in 1981. So people have tried everything under the sun. So they've tried that. We're going to go over just very, very briefly one algorithm that people try to improve these matches. But people have also used like deep learning to learn stereo vision. So you throw two stereo cameras at, or two stereo images at a deep network and see if it can learn to figure out the disparity between the two. And it actually works pretty well. OK, so let's look at another trade-off. Another trade-off is the size of our baseline. So that's how far shifted our two cameras are from each other. So before I was just saying, let's assume we know that. So let's look at kind of the trade-offs between having large baselines versus small baselines. With a large baseline, remember we're dividing our baseline by our disparity. So with a large baseline, we're going to get a better, more accurate measure. But the disadvantage of having a large baseline, you imagine if you have two cameras, imagine the extreme case where I've got a camera over here, and I've got a camera all the way on the other side of the room. They're technically both stereo cameras, but they're both very, very far apart. So you can imagine that the scene they're looking at is going to look very different from two different perspectives. And so doing that feature matching is going to be pretty difficult because the features are going to look just very different. On the other hand, a small baseline, while your features will look more similar, it gives you a little bit less accurate results. So if you imagine here, we're projecting the edges of our pixels. So this is the edge of pixel from one camera, the edge of a pixel from another camera out into the scene. And the area where these pixel edges overlap is going to be actually pretty large. So our true point that we actually care about could be anywhere in here. So we have a lot more variation with closer cameras. So usually what happens when picking what kind of baseline you want for your camera, usually it's the wider the better. So if you noticed on the car, they were about, I don't know, half a meter apart on the windshield. But what we usually decide how big your baseline is the particular application you care about. So if you're on a car, you can put them farther apart because you have a big, wide car to work with. But if you imagine you're working with a little robot that drives around, then you don't have as much space. Or like a drone that's flying around, maybe you don't have as much space to have your cameras as far apart. So that'll usually kind of dictate how far apart you can set your cameras. OK, I did mention before, and you brought this up, there are a lot of failure cases where this kind of stereo algorithm produces bad results. So can we maybe name a few? You guys have any ideas where this will fail? What kind of cases this will fail? So he mentioned if you have bad features. So for example, like we talked about last time with optical flow, if you have the side of a wall and it's moving, it looks the exact same as it's not moving. Same thing for stereo. Yes? OK, so you're saying if the two images are taken at different times, if something moves in the time between you took the two images, then it's going to be difficult to line them up. Yes, that's a great point. Did we have another one? Someone had their hand up. Yes. That's a great one. So if you imagine you're looking at something with a repeating pattern, like say you're looking at a fence, it has the same kind of visual pattern as the fence goes along. It has some really nice features, some really nice gradients. But the problem is, this part of the fence and this part of the fence and this part of the fence all look the same. So if you're scanning along, you can get some false positives. Any other ideas? Yes? Yes, exactly. So if you have an obstruction on one side of the camera and not on the other side of the camera, then there actually won't be any feature alignment between the two. OK, those were all great ideas. So here we'll just kind of show this with some images. So you can imagine here a textureless surface like this wall back here. It's going to be really hard to do the alignment between the wall because you can't really tell which part of the wall lines up to which other part of the wall. It all just looks the same. There's also the case of you have occlusions as well as repetition. So here, again, I think this is a fence. The fence looks the same as this repeating pattern. So you could line up this part of the image with this part or any other part, and it's going to be difficult to do the stereo correspondence. Also, sometimes features look different from different perspectives. So you could have things like specularities. So if you imagine a light in your scene is shining off of one part of a surface, and it looks at one part of a surface for one camera and a different part of that same surface in the other camera, then it's actually going to look visually different between the two cameras. So you're going to get a bad match. OK, so how can we actually improve the matching between these two cameras? Does anyone have any ideas? Like, what could we do to make this better? Yes. Okay, so you could take a lot of pictures over time and average them, so you could get, hopefully, a lot of those issues kind of smoothed out. Any other ideas? Okay, any other ideas? Yeah, so having a shorter baseline will reduce a lot of the effects. So for example, the effect of a specularity. If your cameras are close together, that specularity is going to look to be in the same spot on the surface. So it'll look the same for both cameras. Whereas if they're farther apart, that specularity is going to be in different spots. Yes? Okay, yeah, having more cameras, that's another way. Yes, if you had a lot more cameras, you could say average out or throw out outliers or things like that, and you get a more robust depth. Any other ideas? Okay. Oh, yes. Yes, that is also a good idea. He said if we have context, so if we have, say, you have some good features, could you sort of figure out where the bad features are in between those good features? So if you imagine you're looking at, I don't know, the side of a box. If you're looking at the side of the box, the corners of the box and the edges of the box give you some decently good features, but the center of the box doesn't. However, if you find the depth of each of the edges along one row of pixels, then you can imagine you just say interpolate between the two to kind of smooth out the features in between. That's definitely one idea. That's definitely something people have tried. People have tried all of these. People have tried a lot of things when it comes to stereo. We're going to talk about one of them. So we're going to talk about some more stereo constraints. So before we talked about how we know that our corresponding feature has to be somewhere on this thing called an epipolar line. So it has to be somewhere along a line. So that's one constraint that's imposed by the geometry of the scene. But actually, the scene imposes other constraints that we didn't consider. So one constraint it imposes is uniqueness. And I should point out that these constraints aren't necessarily hard constraints like the epipolar line, but they're softer constraints. Still pretty hard. So uniqueness, so for example, we can't have the same point in one image mapping to two different points in the other image. We also have another constraint, ordering. So for example, if we say we have these feature points A, B, and C, they have to be in the same order in the left image as they are in the right image. So here we see we have A, B, and C, and if we do the matching correctly, so we match up the two A rays, the B rays, the C rays, we get in the left image A, B, C, and in the right image A, B, C. Perfect, perfect. To illustrate this point, let's say instead of matching these correctly, we match them incorrectly. So let's say we hallucinate some point that doesn't actually exist, some point D. So we actually take the cross this line and this line, so we match this feature here with this feature right here. And we hallucinate some point D here that doesn't actually exist. So there's a bit of a problem with this, though. And the problem here is this. On the left, we get this lines up with A, this point lines up with B, this point lines up with D. On the right, we get this point lines up with D, this point lines up with B, this point lines up with C. So you'll notice on the left, D is to the right of B. And on the right, D is to the left of B. So now they're in the wrong ordering, which means that D cannot actually exist as a point. So our feature matching here is wrong. So we can add this as a constraint to our feature matching problem, or it's, yes? Okay, so if you imagine there really is an object at D here, cool. I'm trying to imagine this in my head. Then in that case, right, A, B, D, B, D. You know, I'm not sure. Put me on the spot there. I'll have to think about that. If you want to know the answer, come ask me after class. I imagine it would still work out because I borrowed this from some other people's slides, this specific demonstration. Either that or everybody's wrong, which might also be the case. Okay, so borrowing that problem. There's also one other constraint. This one's a little bit softer of a constraint. They tend to assume smoothness. So we can assume that this disparity changes slowly over time, which basically means that objects tend to be, two pixels that are next to each other are going to be about the same distance away from the camera. That's not always the case. You could imagine here we have the background from Lincoln's arm to the background. It's going to have a big disparity. But in general, you know, if we're following along the edge of Lincoln's coat here, that's going to have a pretty smooth change in depth from the camera. Okay, so I'm actually not going to describe how this algorithm works because it is also quite complicated. But basically, you can imagine setting up these constraints as a graph cut problem. So we basically set up a graph between the disparities and all the pixels, and then we just solve the graph cut problem, and we can line up the disparities. And we build into that graph the constraints that we just talked about here. And what we get are results that look like this. So here, for example, is our before image from before, and there's our ground truth. If we apply this graph cut algorithm, we actually get a much, much better looking depth map here. So you can see there are still errors, there's still problems with this map, but it is not nearly this bad. So we actually get a much cleaner looking depth image than that. Okay, cool. Besides that one question that I can't answer, anyone have any other questions that we'd like to talk about with stereo vision? Okay, we have a few minutes left. I didn't think we'd have time to get to this, but let's talk a little bit about structured light cameras. Cool, so that's what the original Connect 1 uses. So the Connect 1 works by projecting some image in an infrared spectrum out of the scene and then seeing that image in an infrared camera. So what's the difference? Can anyone tell me what the difference is between a projector and a camera? Yes? Exactly. We can use the exact, he said which way the light's going. That is exactly the only difference. A projector and a camera are literally the same thing, except light goes in a different direction. So we can use the exact same pinhole model. So you can imagine when we're talking here about stereo, let me back up to a slide that shows our layout here. Okay, so you can imagine here, when we're talking about stereo, if we say this camera 1 is instead of being a camera, it's actually a projector, and we project some known image out into the scene, then we already know where all of our feature points are, and we already know what all those feature points look like. So we can just do, again, in our infrared image over here, our regular feature matching. And so this is precisely how those structured light cameras work. Are there any obvious problems with how this works? I work with these cameras every day, so I could list off hundreds of problems with how these cameras work. But does anything like come to mind? If we're projecting an infrared light image out into our scene, yes? Yes, so he said if you confuse the sun for the image, so actually these cameras don't work outside at all because the sun outputs a lot of light. You would be surprised how crazy the amount of light the sun outputs is. But if you take one of these cameras outside, it'll completely flood the sensor, so you won't be able to see this image at all. The projector just cannot compete with the sun. So these cameras only work inside. Any other problems? Over there in the corner, yes. Are you saying you're hitting like an angular surface? Yeah. Yes, so he's saying basically if you imagine you're projecting this nice looking pattern and it hits an angled surface, it's going to start looking skewed. Yes, in theory that could be a problem. In practice, that actually tends to work out pretty okay. You will get the case where if you imagine, if your camera's out here and you're looking at a surface that is super angled, you're not going to get, it's going to be way too skewed for your image to see. But in general, kind of slightly angled surfaces still work okay. There is one other problem that is super annoying, and this doesn't work. Infrared light doesn't work on things that reflect infrared light, which are a lot more things than you would think. So basically anything metal or anything that's really dark black kind of absorb this infrared light. Okay, so, and the cool thing about these Connects though is you can actually go buy them if you have or if you have a Connect. Actually, you can't buy them anymore, they stopped making them, but you can still get them on eBay. Okay, cool. Does anybody have any other questions before we are done for today? Okay, that's all I have for you guys. Hopefully that wasn't too confusing. If you have any questions you'd like to ask offline, come ask me on Mattermost, ask Joe. Have a good day.